An experiment was performed 200 times to assess the probability of a successful outcome. The number of successful outcomes was 72. So we had 200 trials, of which 72 were successful, which means that the other 128 trials were unsuccessful, or they were failures, because each trial can either be a success or a failure. We are required to find a 95% confidence interval for P, which is the probability of a successful outcome, and also we must find a 99% confidence interval for P. Recall that of the 200 trials, 72 were successes. That means that our sample proportion, P sub S, is our sample proportion. That is equal to the number of successful outcomes, which was 72, divided by the total number of outcomes, the total number of possible outcomes. That's, in other words, the number of trials. 200, 72 over 200 is 0.36. So our sample proportion for the successes is 0.36. Therefore, the sample proportion of the number of failures, that's 1 minus P sub S, which will be 1 minus 0.36, and that will be 0.64. So each trial can either be a success with a probability of 0.36 or a failure with a probability of 0.64. We want to calculate a 95% confidence interval for P, the probability of a successful outcome. So P is actually the population proportion. We can use our sample proportion as an unbiased estimate of the population proportion, assuming that our sample is representative of the population from which it was drawn. So confidence interval for population proportion P is equal to, so it's going to be symmetrical about the sample proportion. To the sample proportion, we're going to add or minus Z star, which again, that value varies according to the confidence interval. For a 95% confidence interval, Z star will be 1.96. Right? Plus or minus Z star by the standard error will be given as P sub S by 1 minus P sub S over N, the number of trials, which in this case is 200. So this would be equal to, our sample proportion is 0.36 plus or minus Z star will be 1.96 for our 95% confidence interval, and we recall the value of P sub S is 0.36 times 0.64 is 1 minus P sub S divided by 200, the number of trials. So that would work out to 0.36 plus or minus, this is going to be 0.0665. So our lower bound would be 0.36 minus 0.0665, and our upper bound will be 0.36 plus 0.0665. That is equal to, so 0.36 minus 0.0665 is 0.2935, and 0.36 plus 0.0665 is equal to 0.4265, and there we have our 95% confidence interval for the population proportion. So we are 95% confident that somewhere in this interval, somewhere between 0.2935 and 0.4265, lies the actual value of the probability of a successful outcome. Somewhere in this interval, that value should lie. We are 95% confident of this. For part B, we want to obtain a 99% confidence interval. So we want to be even more certain, more assurance. We want more assurance that we are going to capture within our calculated interval the true value of the probability of a successful outcome. So again, P is equal to, and we already have it here, that's equal to the sample proportion plus or minus Z star, which again, that's the only thing that's going to vary here. Z star for a 99% confidence interval is 2.576 by the root of P sub S by 1 minus P sub S over N. That's not going to change. So the only thing that's going to change in this case is our Z star. So P sub S is 0.36 plus or minus Z star. Now, because we want more assurance that our interval will capture P, Z star is going to take on a greater value. So Z star was 1.96 for a 95% confidence interval. Then for a 99% confidence interval, it's actually 2.576, which makes sense. We need it to be larger so that our interval will be wider. A 99% confidence interval will always be wider than a 95% confidence interval, and similarly a 95% confidence interval will always be wider than a 90% confidence interval. Right, so this is going to be just as it was in part A, 0.36 by 0.64 divided by 200. So our confidence interval will be 0.36 plus or minus. This is going to work out to 0.0874, which is larger than the value we got for a 95% confidence interval, was only 0.0665. Now it's increased to 0.0874. Of course, that's because Z star takes a greater value on our 99% confidence interval. So this is going to be 0.36 minus 0.0874. That will be our lower bound, and 0.36 plus 0.0874 will be our upper bound, and that is equal to 0.2726 up to 0.4474. So we are 99% confident that somewhere between 0.2726 and 0.4474 lies the actual value of the probability of a successful outcome. So both for the 95% and the 99% confidence intervals, the interval is actually symmetrical about the sample proportion 0.36. So you can check for both of these. 0.36 lies exactly in the middle. But for the 95% confidence interval, it was narrower than the 99% confidence interval. And again, as I explained before, the reason for that is if we want more assurance, if we want greater assurance that our interval captures the actual value of the probability of a successful outcome, that is P, the population proportion, then it must be wider. And that's why for a 99% confidence interval, Z star takes on a greater value, 2.576, as opposed to a 95% confidence interval where it takes on The smaller value, 1.96.